You may have wondered why a thrown object always appears to travel in an arc shape, or in the case of a bouncy ball, in several arcs. This phenomenon is called projectile motion, and it is experienced by objects thrown near the Earth's surface. The object's velocity is a combination of two components, its vertical velocity and its horizontal velocity. Since the object has inertia, its horizontal component of velocity remains constant. In other words, there is no acceleration in the horizontal direction. However, the vertical component of velocity changes over time, because of the downward acceleration due to gravity at the Earth's surface. This is what causes the arc shape. You can observe the ball's changing vertical velocity because the higher it gets, the slower it ascends, and the lower it gets, the faster it descends, since the force of gravity is contributing to its velocity. The vertical and horizontal motions' independence from one another can be observed by rolling an object off of a table, and comparing this to when you drop it from the same height. As you can see, at each point in time, the objects have fallen to the same height, since the only acceleration occurring is downward because of gravity. Here we can examine a bouncy ball to understand the different aspects of projectile motion. The distance between the lines on the paper both horizontally and vertically is 5 centimeters. We can see here that the point of launch for the ball is at about 15 centimeters, and time is at 0 seconds. The ball reaches the maximum height, which is the highest point in its arc, at about 0.33 seconds, and it reaches a height of about 55 centimeters. This will be more relevant later. The ball lands at approximately 75 centimeters on the horizontal at the 0.67 second mark. One thing we can derive from these measurements is the horizontal component of velocity, and we can use the equation where the final horizontal position equals the starting horizontal position plus the initial horizontal component of velocity multiplied by the total time. When we plug in these values, and we have to be careful to convert centimeters to meters since velocity is measured in meters per second, we get 0.90 meters per second for the initial horizontal component of velocity. So this is basically how fast the ball is moving initially in the horizontal direction. Because the horizontal component of velocity remains constant, we know that at any point in the object's path, the horizontal velocity will be 0.90 meters per second. Next, we can figure out the vertical component of velocity using the equation that the final height equals the initial height plus the initial vertical component of velocity multiplied by the total time plus half of the acceleration due to gravity times the total time squared. Generally, the acceleration due to gravity at the Earth's surface will be 9.8 meters per second squared. We plug in these values and the ball returns to the same height as it began at, so the beginning and end y values are both 0. We get 3.28 meters per second for the initial vertical component of velocity. So this is basically how fast the ball is moving right as it launches in the vertical direction. Since we now have both initial components of velocity, we can calculate the overall initial velocity. To do this, we can use the Pythagorean theorem. In this case, a and b squared will be the vertical and horizontal components, while c squared will be the overall velocity. After we plug these values into the equation, we get 3.4 meters per second for the overall initial velocity. Now we can also find the angle at which the ball launches from the ground. One way is by using the initial horizontal component of velocity, which is equal to the initial velocity multiplied by cosine theta, theta being the angle. When we do this, we get an angle of 74.7 degrees. We could also use the initial vertical component of velocity, which is equal to the product of the initial velocity and sine theta. When we do this, we also get 74.7 degrees. This demonstrates how, as long as if you have two of the velocities, you could use either of these equations to obtain the angle. When we overlay a protractor on the video, we can see that the value of 74.7 appears to be pretty accurate. We can also test our accuracy by calculating the maximum height of the projectile. This is equal to the initial velocity squared multiplied by sine theta squared and divided by 2 times the acceleration due to gravity. We get 0.55 meters, and this is what we observed in the video as well. As you can see, with just a few measurements, we can predict numerous characteristics of the motion of a simple bouncy ball. These same principles can be applied to a diverse range of objects, from bullets and small everyday items to cannonballs and rockets.
Where is my soul?